Hi folks, we're going to take a look at number 6 from the Unit 5 assignment sheet. So here they're essentially testing the resistance of a product with respect to the temperature, and they're putting it in some kind of environment that goes from 120 degrees Celsius to negative 60 degrees Celsius, so fairly extreme temperatures. And they tell us that they want us to start our model when it's at 30 degrees Celsius and initially decreasing. So I suspect that's going to help us determine the apparent function and phase shift if we need it, but we'll wait for that later on. We have our max and min, so let's start with that here. So our max is 120, our min is negative 60. So from here we can calculate our A value and our C value. So our A value is 120 minus negative 60 divided by 2. So that's going to be 180 divided by 2 is 90. And then our C value is going to be 120 plus negative 60 over 2. So that's 60 over 2 is 30. Okay, now it tells us that it takes 12 hours to change from the maximum to the minimum. Okay, so that does not represent a full period, but represents half the period. So our period is actually going to be 24 hours. So that means that our K value is going to be 2 pi over 24 or pi over 12. Okay, so now let's figure out what our parent function should be. And I notice here that at time 0 seconds, we're starting at 30 degrees Celsius, which happens to be exactly where our axis is located. So we think what function starts at the axis, it's sine. But something very important to notice is that it says that we're starting at 30 degrees and decreasing first. Okay, so since we're starting at our axis, okay, and we're decreasing first, that means we're going to have to use negative sign. So our parent is going to be y equals negative sine x. And the good news is that we don't need a phase shift. All right. So let's now write out our model, which we can do here. So we have y is equal to negative, and the A value is 90. Sine of our K value is pi over 12. And we don't need any phase shifts, so that's just going to be x plus our C value, which is 30. Okay. Now, what it tells us here is that the product is expected to experience difficulty when it is below negative 40 degrees Celsius, and determine the times of concern in the first 2 days of testing. So this is interesting here because we're not actually solving a trigonometric equation. We're solving a trigonometric inequality. We're trying to determine when the temperature is less than negative 40 degrees Celsius. Okay, but we're going to solve this inequality the way we solve most of our inequalities, which is to determine the X-intercepts of this equation here. So what we're going to do is we're going to solve for the X-intercepts, and then from there determine which intervals meet our conditions. So I'm going to start by solving negative 90 sine of pi over 12x plus 30 equals negative 40. So let's actually determine when it's equal to it, and then from there we'll be able to determine the intervals where it's below. All right, so let's step number 1. So now that we have an equation, step number 1 in our algorithm is to isolate the sine ratio. All right, so here we're going to bring the negative 90 to the other side, the 30 to the other side, and then divide by negative 90. So what do we have here? We have negative 40 minus 30 is negative 70 divided by negative 90. So that's just going to be 7 over 9. Okay, so again, negative 40 minus 30, negative 70. Negative 70 divided by negative 90, it's going to be positive 7 over 9. Okay, this does not relate to a special angle, so I'm going to have to use the inverse sign to solve this. So step 1 was to isolate our trig ratio. Step 2 is to determine our 2 solutions in the first cycle. So we have pi over 12x can be equal to either inverse sine of 7 over 9. So let's calculate that. Inverse sine, let's turn it on. Inverse sine of 7 over 9, which is 0.89. Okay, or now since we're working with sine, it's going to be pi minus this number. So the other option is going to be pi 3.14 minus 0.89, which is 2.25. All right, step 3 is to isolate for x. So here I'm going to multiply by 12, divide by pi. So 0.89 times 12 divided by pi. Okay, that gives me 3.4. Or let's do the same thing with the 2.25. 2.25 times 12 divided by pi. That gives me 8.6. Okay. And so these are my first set of answers. And then step 4 is to determine other answers by adding the period. So the period, remember, was 24 hours. All right, but we're only looking at the first 2 days of testing, so we don't want to go over 48. So if I take 3.4 and I add 24, we get 27.4, so we're still good. But if I try to add another 24, well, I'm going to end up, here if I do plus 24, we end up above 48 hours, so I stop there. So same thing here, 8.6 plus 24 is 32.6. And again, if I were to add another 24, I'd go beyond. Okay, so these are the only times I'm interested in, but I'm not interested in when it's equal to negative 40. I want to see when it's less than negative 40. So again, here, I'm going to draw a graph. So I've got my negative sine function, and I've got 2 cycles of it. Okay, and it has to be less than, say, negative 40. Okay, and we see that it's going to go below negative 40 after the first time, and then come back above after the second time, and then again from 27.4 to 32.6. So our solution here is that x is in, okay, so since it has to be strictly below negative 40, I'm going to use open brackets to not include these. Okay, so here 3.4 to 8.6, so in this interval here, and then also including 27.4 to 32.6, and here x is in, I guess we're working in hours. Okay, and so there are our answers. Okay, so just to recap, step number 1 was to come up with our model. In this case here, we didn't need a phase shift because we were starting at the axis and going downwards first, so that's why we use negative sign. Okay, then I realize I'm solving a trigonometric inequality, so I start by solving the equation and then so I follow my my algorithm for solving the equation, and then from there I can use the graph to determine what range of values I'm interested in to answer this question. Okay, that's it for this one.